In this tutorial, we will be discussing solutions. So a solution is a homogeneous mixture, which means that the liquids or the solute and the solvent are mixed evenly throughout. So if you think about it as like a sugar-free Kool-Aid, where no sugar settles to the bottom of it. The first drink of Kool-Aid and the last drink of Kool-Aid should taste the same, and that's because it's a homogeneous mixture. The Kool-Aid is spread throughout the jar. Something that wouldn't be a homogeneous mixture would be like peanut butter. If you open up a jar of peanut butter, you'll find some oil residue at the very, very top. It's separated out. That is not a homogeneous mixture. These form when the sufficient attraction between the solute and the solvent molecules exist, meaning that they're attracted to one another. And this goes into the idea of like dissolves like. They need to be able to interact. And we're going to look at this phrase again later. They have two components. One's a solvent and one's a solute. The solute is much smaller than the solvent. So you're always going to put the lute in the vent. You're putting the solute into the solvent. These solutes can be solids, liquids, or gases, and they spread throughout the solution very evenly. So at the beginning, at the end, top or bottom, left to right, it doesn't matter at all. It looks the same. It's the same quantity of particles. The solute and the solvent have the same physical state at the very end. It may not have the same physical state at the beginning, but it will be at the end. You cannot separate these by filtration. You can evaporate them, but you will not be able to filter it out. Think of coffee. Once you put the water through the coffee, it comes out to be brown water. You can't filter out that brown. You can boil it, you can forget to take it off the pot, and it ends up boiling off the water and the brown residue's left, but you can't filter it out. And you can't see the individual particles, although it might give a color, once again like that brown coffee. So here's another example of copper sulfate. Notice that it's blue in here. That's the color of copper sulfate. If you look on the right hand side, the whole container looks blue rather than just the bottom of it. That's purely because of the solute being mixed evenly throughout. So when we're looking at the solutes and the solvents to make the solutions can be any physical state, solid, liquid, or gas. And it can be a combination of physical states to begin with. For instance, air is a combination of oxygen gas and nitrogen gas. Where if you look down at the bottom, brass is actually zinc and copper mixed together. It's actually a homogeneous mixture of zinc and copper. You just don't think of it that way because it's a solid and not a liquid. Water is a very good solvent. In fact, it probably dissolves 80% of what's in our world. And it all has to do with the types of bonds that they have. So if we look here, here's H2O, and we look on the periodic table, oxygen's around here. It's really close to fluorine. It's very electronegative. So the electrons are going to tend to drift towards that oxygen, making that oxygen partially negative. This symbol here is the shorthand for the word partial. So you'll see here it's partially negative. That hydrogen then becomes partially positive. It's a slightly positive charge. And so those positives and negatives interact when it comes to dissolving chemicals. In order for something to dissolve, here we have part of a solution, here we have part of a solution before it's mixed together. The interactions amongst these molecules need to be broken up. So those interactions have to stop, so that way it can actually interact with the other chemical. And same with the chemicals up here. these chemicals up here are interacting, and those interactions have to break in order to interact with the things underneath. So the solute-solute interactions and the solvent-solvent interactions have to be broken. And this interaction here, the solute-solvent, the particles that you're trying to mix together, they have to be strong enough to overcome the initial attraction, to be able to break that. Now I said the words like dissolves like earlier. We can actually put this on a continuum of nonpolar through ionic. Everything else in here is polar. Water is polar, so water can actually dissolve all of this. The only thing it can't dissolve is that nonpolar region. So basically what that's meaning is that with polar and with ionic, there's actually a difference in charges. There's a positive side and there's a negative side, which is why it's called the poles. On the nonpolar end, you're not going to have that positive and negative side. You're going to be wanting to look at the electronegativities. So when we're looking at the atoms, and that's why we went over this at the beginning of the year, the atoms that are closest to fluorine are the most electronegative. And if there's a difference in those electronegativities, then you're going to either have an ionic or a polar compound. And the difference between those charges or a lack of those charges will dictate whether or not something will dissolve. For instance, if you have a polar solute and a polar solvent, those will dissolve in each other. If you have two nonpolar things, those will dissolve in each other. However, let's say, for instance, the solute is an oil, for let's say olive oil or Italian dressing. That's nonpolar. And if we try to dissolve that in vinegar or water, it's not going to mix. You're going to see different levels. You're going to see a line. So here we have sodium chloride that's being dissolved in water to produce the ions sodium and chlorine. This bond here needs to be able to break and interact with that H2O. If you look here, we have chlorine ions. Chlorines are negatives. So notice that they drew that hydrogen closest to the chlorine. That's because hydrogen is partially positive. That partially positive is going to interact with that negative. It's going to be attracted to each other because the charges then attract. If you look on the other side, here's sodium. Sodium is positive. Notice that they have the oxygen closest to the sodium. And that's once again is because we're having the positive and the negatives interact. That's why when we look down here, this positive sodium's in the middle. It's surrounded by negative oxygens. We have the negative chlorine in the middle. We're surrounded by positive hydrogens. That's called solvation. So here's another example. We have methanol and we have water. And then on the right hand side, we have the two coming together for a mixture. Remember, the red is partially negative and the white is partially positive because that's water. If we look over here, we have that same red and the same white. So we're going to have a positive-negative interaction here too. If we look over here to the far right, the negative on the methanol is being attracted to the positive of the water. And that's happening throughout the entire mixture. The positive and negatives are interacting. So let's take a step back. Identify the solute for each of the following solutions. 2 grams versus 100 milliliters. 2 is smaller, so therefore that's going to be our solute. 60 milliliters versus 30 milliliters. 30 is smaller, so that's going to be our solute. 55 milliliters versus 1.5 grams. 1.5 is smaller, so it's our solute. 200 milliliters versus 800 milliliters. 200 is smaller, that's our solute. When solid LiCl is added to water, it dissolves because, let's look at the Li. Li is a plus sign. That means it's going to be attracted to the negatives. here's our water, partially negative, partially positive, is going to be attracted to that negative portion. So the answer is this one, the oxygen atoms to the partially negative water. Cl- is the exact opposite. We're looking at this compound again. The chlorine is negative. That means it's going to be attracted to the positive, which means it's going to be attracted to the hydrogens. Which of the following solutes will dissolve in water? Water, once again, is polar. It will dissolve in anything that's polar or ionic. Sodium sulfate is ionic, so it will dissolve. Sodium is a +1. Sulfate is a -2. Because of that positive negative, it's going to interact with the water. Gasoline, they tell you, is nonpolar. Because the gasoline is nonpolar and the water is polar, that one will not dissolve. Iodine, same situation. I2, there's no difference in electronegativities here because it's the same thing. Therefore, it's nonpolar. There is no positive negative interactions here. HCl, if we look on the periodic table, these are two different elements. Cl is here, H is here. Chlorine is closer to fluorine, so the electrons are going to be drifting towards the chlorine. Because there's a difference in electronegativities, we have a partially negative and a partially positive end. Therefore, it's going to interact with the water.